Hello, and welcome to episode 1 of our lesson in science. Today, we're going to be covering the basics of the scientific method, as well as the different basic branches of science and the differences between a hypothesis, theory, and a scientific law. So, we're going to begin with the types of sciences that you can encounter. So, there are many branches of science that are under the purview of many of these sciences, but mostly we're going to focus on just the overview of every single branch of these. So you have life sciences and earth sciences is really two big ones. And life sciences obviously is the study of organic life forms and organic materials and how they interact with each other as well as the world around them. And that's where we have like biology is pretty much the life science because you study life and how it interacts and reacts with the environment around it. And you can also have like anatomy and physiology for more advanced studies, mostly specifically about, human bodies and how the human body functions, what different parts of the human body are supposed to do, things like that. You can have like veterinary medicine and stuff like that is a much more specific thing with biology. It'll be a much more specific, tailored approach to learning how animals' bodies work and how to treat various ailments in animals. And under the earth sciences, well, you're basically studying anything that's not organic, which is quite a large amount of the world around us, but also the universe around us. So the study of inorganic things and inorganic materials can also just be referred to as earth sciences. And in the earth sciences, you can get into more specific fields that like geology or you can look at chemistry and physics. Really, if you think about it, would be under an earth science because they are looking at non-organic compounds and materials and non-organic compounds and materials and how they interact with each other. So that would be what your earth sciences are. And then obviously we have our physics and chemistry. Well, physics is going to study the universe at its smallest levels, is really what physics is trying to understand. The universe on the smallest levels is, and how that interacts with each other, but how it also coalesces into larger pieces. That's where chemistry comes in. Because chemistry, we analyze molecules and how atoms bond together. Physics, we try to understand how the larger picture that we can see around us everywhere comes from the smallest parts, right? So you have the smallest functioning unit of matter is an atom. A single atom is the smallest functioning unit of matter. However, as we've come to understand more in-depth things about matter, we've come to realize that there are subatomic particles, like quarks, for example, that actually make up the atom's individual parts. And so are even smaller foundations for matter. However, they don't have a measurable mass because they're so small, we can't actually accurately measure their mass. So we're left, the same problem occurs with electrons, actually. The atomic weight that you're going to encounter for most of the periodic table, that is how we organize the periodic table, like all the 1, 2, 3, 4, and all that stuff is their atomic weight. And usually, their atomic weight is going to be more based off of their protons and neutrons that are in the nucleus, and the electrons are just a guess. Their size is so much smaller than the corresponding protons and neutrons that are in the atom, that it's harder to get an accurate measure of what their actual weight for the purposes of the atomic weight would be. But I digress. Back to the topic of physics. So when we understand the basic blocks that build up our entire universe, we hope to understand better how that universe comes together. But once again, like I said, physics, while it can explain the larger parts, it doesn't necessarily explain the relationship between the smaller parts. And that's where chemistry comes in. So, yeah, physics, you can look at a big picture and see that, like in the theory of general relativity, where Einstein states that the effect that we call gravity is not actually a force, it is a result of the bending of what we colloquially know as the fourth dimension or space-time. That warping of space-time is what we feel as the force of gravity. And in order to prove that, Einstein visited a man known as Alfred Hubble. I do believe his name was Alfred, but Hubble, a scientist known as Hubble, who is obviously the namesake of the Hubble Space Telescope. And the two of them conducted an experiment that they intended to do, observing a solar eclipse. But when every solar eclipse they attempted to view was not working out for them, they ended up artificially creating a solar eclipse with something to block out the sun on their telescope. They ended up being able to see stars that should have been directly behind the sun were appearing around the halo of the corona for the solar eclipse, thus proving that you feel gravity, but it's actually the warping of space-time. The stars being directly behind the sun, but somehow being visible around the sun, proved that space and time warp around massive objects. And so you'll be able to see objects that you wouldn't otherwise be able to see because of the distortion that gravity and the force of gravity that we feel causes. And so, like I said, physics can't explain the larger parts of the universe, but it's best at understanding individual parts of the universe and their relationships with each other, so that you can understand how that coalesces into the larger whole. Now, the actual acting of that coalescence and how molecules interact with each other is where chemistry comes in. So, on the periodic table, the first two columns, right, are alkali metals and alkaline earth metals, right? And both of these groups are extremely reactive with water. And chemistry helps to tell us why, right? But chemistry is also really good at telling us about biology, since now we know that life sciences aren't totally separate from, are not totally separated from the non-life sciences. The earth sciences and such are not totally separate from biology. In fact, all of these sciences are so tightly interwoven together that if you ignore one, many things won't make sense in the larger context of these other sciences, right? So, there's your basic introduction to different branches of science and how they interact with each other, as well as like what we're going to specifically be getting into as we go along, right? So, next we're going to cover the scientific method. So the scientific method is a basic path to follow for inquiry into observations that you make about everyday occurrences or even some more rare occurrences. You want to find a logical explanation for something, then the scientific method is how you are going to explain what your observations are and what they mean in the larger context, right? So the scientific method, you separate out personal biases and your emotions. If you're going to get an accurate result, your emotions mean nothing to science. And that's really one of the things that's the hardest for scientists to do. And in fact, it is impossible for scientists to separate themselves and their personal ideas from their theories. There are so many theories that do not work, that you cannot observe anything for. And I shouldn't even say theories, because mostly they are hypotheses. They have dreamt up and they can't prove, but because they are so invested in the idea that they've created, they can't ignore it. So there is that unfortunate segment of the scientific community, which is the majority of the scientific community, that are more interested in validating their own hypotheses at the expense of the scientific method. That it's very rare to find scientists that are capable of separating their own biases and their own desired outcomes when it comes to testing their theories and hypotheses, as well as when it comes to devising them in the first place. So the scientific method is as follows, really. You make an observation about something around you and ask a question about it, right? This first step, that observation that leads to a question, it is really one step, because you're maybe sitting in your sitting on your porch, right, or taking a walk through a park, and you see all the leaves on every tree that you can see in the middle of summer are green. So you say, hey, I think all leaves on all trees that bear leaves are green. Because every tree that I am seeing has green leaves. I'm going to say, well, then isn't it true that all leaves on every tree are green? That's where the observation comes in, and you make the observation and you ask the question. So you've seen a condition that you think is true, and now you ask a question in order to make it into a hypothesis that you can then test. So the hypothesis that you've got from your observation and asking the question is, are all leaves on all trees green? And then you test the hypothesis. Well, in this case, the test isn't necessarily, setting up a whole Rube Goldberg device where this machine knocks over that machine, that knocks over that machine, that moves this machine to go spinning around like this, and so on and so forth. Right? For this particular hypothesis, so I'm going to write the hypothesis up here. Since I saw that all the leaves are green on all the trees in the park, all tree leaves are green. Now, I could take it a step further and say, like, oh, well, obviously, in fall, or autumn, whichever you prefer to call the season between summer and winter, in autumn, all the leaves turn, yellow, orange, red, brown, purple, etc. So this is false at that time of year. So I could take it even further and say all leaves on trees that are not, preparing to shed them for winter are green. but we're just going to go with all tree leaves are green. So either when I test the hypothesis, I can say when autumn hits, that's not true. So autumn means no, basically, is, but also I have to make observations and specifically look for trees, and this is how you test it. So for the test, look for trees with non-green leaves. Right? So this isn't necessarily a test in the traditional sense of like testing a hypothesis where you have to, you know, like if you're trying to figure out in chemistry testing a hypothesis on, let's say, lithium. Lithium is reactive with water, would be the hypothesis, right? And lithium generates an explosive reaction with water, would be like a hypothesis. And all you have to do then is have some lithium, have some water, and, you know, set up a safe way to put the lithium in the water to watch the reaction. That's what a lot of people will think of when they hear the word, or when they hear the phrase testing a hypothesis. They'll think, oh yeah, all I need to do is have, you know, some laboratory experiment to find out if all the leaves on all trees are green, right? But in reality, many hypotheses out there are not testable in a laboratory environment. Many hypotheses are simply testable by making an observation out of nature. And really, that's what some of the most accurate understandings and some of the scientific laws that we have today, in fact, all scientific laws that we have today, come from making observations of universe around us and of nature. So all the scientific laws that you can think of, we've made observations of them, and the observations support that really you can't destroy matter, right? That's one of the big ones. So, and we'll go over the scientific laws when we get to that portion, but we made observations that end up supporting these scientific laws, and that's, you didn't really test the scientific law, you're just trying to quantify it. And that's where, like, Sir Isaac Newton came in with actually creating a formula for measuring the gravitational effect of an object, right? But I digress. Let's get back on track with the covering of the scientific method. So now that we're at the testing the hypothesis stage, well, now I need to, since the world's way too big for me to reasonably be expected to travel every single part of the world in order to see if I can find a tree that has leaves that are not green, right? The world's way too big for one person to travel all that way. Now, obviously, there are also a lot of trees that we know that don't have green leaves. But let's say that I live in a place where all the leaves on every tree is green. Are green, sorry. Well, then obviously I'm going to need to do some traveling to find that. But I test the hypothesis by traveling and by looking for trees that, specifically looking for trees that do not have green leaves. Okay? So that's one of the biggest mistakes that most people make when it comes to the scientific method. You're always, for testing your hypothesis, you always test with the intent to fail. Right? And that's why when it comes to the scientific method and testing your hypothesis, people that are directly adversarial to your position are going to be the absolute best to test your position. Because if your position can stand up to scrutiny from somebody that is actively trying to disprove your position, then your hypothesis is going to be more likely to be correct. If it can withstand scrutiny that is designed to disprove you, then it will stand up to any test that will be designed to, support the hypothesis. Any test that's designed to support the hypothesis will be infinitely less useful than the tests devised to disprove the hypothesis, right? So whenever you test the hypothesis, always be adversarial to the hypothesis. You always take a position that the hypothesis is wrong, okay? You always test it like the hypothesis is wrong so that you can find the most accurate answer to the hypothesis. So in the case that all tree leaves are green, the test is look for non-green tree leaves, right? The test isn't count how many trees that you find that have green leaves. The test is look for one example, because all that hypothesis needs to be false is one word. One word being false makes the entire hypothesis false. And so all you need is one tree that grows consistently with non-green leaves, and you've proven that hypothesis false, because now all is no longer able to be used to encapsulate all trees, because obviously, like I said, not all trees. So after you test the hypothesis, now you observe the results, which is, in this case, have I found a tree that doesn't have green leaves? And yes, it'll be like an autumn blaze maple, or various maple trees don't have green leaves. You will have like some dogwood trees and stuff like that. So you observe the results, and the results clearly say that the initial hypothesis is false. So you observe the result. The observation, so let's say observe false. And so now the step that a lot of people seem to leave out for some reason, and this is going to really change whether or not you actually get anything out of the scientific method, is step 5, change your hypothesis as needed, right? So sometimes scrapping the entire hypothesis is a good thing, right? So you say all tree leaves are green, well, just scrap the entire hypothesis. Because really, at the end of the day, one, it's not so important as to how much of the trees are green. It's more an important question of why are the tree leaves green, right? So maybe the hypothesis was asking the wrong question, or maybe the hypothesis was just kind of a frivolous pursuit anyway. You have to be able to discard the hypothesis if it's not necessary. But if you want to continue, you can also just change the hypothesis. So you can say, trees' leaves are green, many tree leaves are green. Well, now that hypothesis is true, simply because you're not giving a quantitative amount. And that's another couple words that I need to throw up here to talk about here in a moment. So I will write those up here. But in this case, we'll discard the hypothesis. But let's say I have another hypothesis in relation to, let's say, let me go ahead and write these words up here that we'll define in a minute as well. So you have quantitative and qualitative. And these are both forms of measurement. Right? But let's say I have a more daring venture to have a theory or hypothesis on. And the hypothesis in this case, let's say, dark matter doesn't exist. Or, well, actually, and this is another thing that a lot of people make a mistake on, right? You can't prove a negative. You cannot prove a negative, okay? Negative statements, all it takes to prove a negative statement is to have anything at all to prove otherwise, and the negative statement no longer works. So in this case, the best thing to do would say dark matter exists. If I want to prove that dark matter doesn't exist, then all I need to do is test adversarially against the theory that dark matter exists. And one of the best things to point out when you test adversarially to the notion of dark matter is that there is no method that we have devised or that we have organized or that we have done anything with that has proven, that has actually observed dark matter or that has actually been able to measure dark matter. Everything that we have done to measure dark matter and everything that we have done to locate dark matter has failed. So now I can make the observation that it's most likely that dark matter doesn't exist based on tests. So the hypothesis after testing, the observation is most likely not. Can't say with absolution, though. You can never say with absolution that something does or does not exist, because the moment you say it with absolution, you find any indication, and there you go. You've disproven your hypothesis once again. But it's most likely that dark matter is a failed hypothesis. It's not even a theory, because the theory of dark matter would require that testing and scrutiny and also observations have somehow proven dark matter, when in reality dark matter, there has no capability to prove it, because the dark matter is, its relationship with the universe is way out there. It's not being observed and talked about in ways that make sense. It's being observed more dogmatically. So dark matter is most likely not to exist, because everything they use to describe dark matter would describe the God that they are so, adamant to disprove. Well, dark matter behaves just like God does, really. You cannot directly observe dark matter. So you have to find something that you can observe that is directly related to dark matter in order to observe dark matter. But you can't look at dark matter directly. The only way you can observe dark matter is its effect on the universe. And it's also everywhere, all around us, maybe even passing, through areas that we're living in. And so, once again, like I said, dark matter as a theory does not hold up to scrutiny. And it's not a theory. Based on the concept of theory, hypothesis, and scientific law, it's not even a theory. But we'll get into that. So, in the idea of dark matter, you'd have to devise tests that will make it so you can actually observe something that apparently cannot be observed. And something that apparently you have to also be able to measure something that apparently cannot be measured. Kind of a flaw. Now we change the hypothesis as needed, and eventually we can continue. This is the other one, you know. This is 5 and 6 are very important. You change the hypothesis as needed, and then 6 you continue steps 3 through 5 until no more changes are needed to the hypothesis. And then 7 you share the result. At the end of the scientific method, the goal is to go from hypothesis to theory. Because this is a hierarchy, right? So this is step 1, this is step 2, and this is step 3, right? The goal of the scientific method is to take a hypothesis and turn it into a theory. You're trying to prove a theory from your hypothesis. Your hypothesis, if it stands up to scrutiny, will eventually be a theory, which means that you'll be able to recognize it in more circumstances than, say, just making a casual observation standing on your front lawn. Now you'll actually have a scientific consensus on things, right? So, the scientific method, the goal is to go from hypothesis to theory, or to disprove a hypothesis. Because, as I said, really the scientific method should always be adversarial to the hypothesis. It should never be friendly. So, scientific method, let's write this up here. SM should always be adversarial to hypothesis. Always test your hypothesis to attempt to fail. Because if you're testing it to prove it, if you're testing it to succeed and prove yourself right, you're not testing it. You're seeking validation. And once again, this is why I said the scientific method, the best way for the scientific method to work is to try your best to avoid biases and to only test to try to make it false. Always try to prove yourself wrong. Never try to prove yourself right. Always try to prove yourself wrong. At any point in time, if anything I've written on the board helps you out with anything, please feel free to take a screenshot of the screen while you're watching the video and save it for later, right? Now, moving on from the scientific method, we're going to go into the hierarchy of, scientific questions, right? The hierarchy of questions and where they fall in terms of testing as well as accuracy to the world and universe around us. And so you have a hypothesis is the basic building block, then you have a theory, and then you have scientific law. So a hypothesis is just a basic, you're basically making it's always given this way, but an educated guess. That is what most people shorthand the definition of a hypothesis into, an educated guess. So you make an observation and you estimate or guess based on your observation. You guess at the nature of something, right? So the hypothesis is the first thing that you need to have really to begin the testing process of the scientific method. So the scientific method, you make that observation and form the hypothesis. Second step of that is forming the hypothesis, and after you get the hypothesis in there, right? Then you keep testing and testing and testing, and like I said before, we continue all these steps until you share that result. That sharing of the result, once your hypothesis holds water, once your hypothesis is no longer being disproven with more tests prove your hypothesis correct, and once again, adversarial tests, right? So more of these tests that you're doing are adversarial to your position, but are also proving it correct. So now you've got a bunch of tests that are designed to make your experiment fail, designed to make your hypothesis fail. More of the test results are coming back in the positive than in the negative. Or, in the case of some hypotheses, all of the test results are coming back positive and none or such a small number of them are coming back in the negative that the hypothesis is pretty much proven. So, when you get a majority of the time that your hypothesis is proven correct after you've updated it, changed it, and continued to test it, eventually you hopefully have got it into a working theory. And a theory is a more informed hypothesis. So, hypothesis is an educated guess. Well, then a theory is a reformed, refined, and well-tested hypothesis. So you continue to test and test and test and test your hypothesis until, once again, like I said, the majority of the time, or an almost absolute amount of the time, the hypothesis is correct, at which point it falls under peer reviews, and once it gets into the scientific community and they actually start reviewing it themselves, then it will most definitely be tested adversarially. But the theory is basically just a reformed, refined, and well-tested hypothesis. You've gotten a lot of tests under your belt, and you have had other individuals that are completely separate from your tests and your hypothesis that have tested your hypothesis. And now individual tests, and not even, a majority of individualized tests made by multiple different scientists are proving your theory correct, or your hypothesis correct. Now it's a theory. And so it moves up in the hierarchy to the second step of theory, right? And now that you're in theory, the next step would be hopefully making it into scientific law. But we only have a handful of scientific laws because there are only a few things that have been proven to be true with such a close percentage to 100% of the time that it may as well be 100% of the time. So you have the 3 laws of physics that Sir Isaac Newton created mathematical formulas for, or observed and made accurate observations of. So you have the laws of physics of the law of inertia, equal but opposite reactions, right? Everybody knows that one. Every action has an equal but opposite reaction. That's the law of inertia. Sorry, that's the law of equal but opposite. The law of inertia is any object in motion will stay in motion until acted upon by an unbalanced force. And any object at rest will remain at rest until acted upon by an unbalanced force. And in this case, unbalanced just means that, so for the laws of physics, right? For the law of inertia, so you have an object, let's say a box, An unbalanced force simply means that the force going in any one of these directions is greater than the forces in the other directions, right? And so long as these are all balanced, the object stays where it is, right? But the moment that you get a little bit more force going in this direction, the object is going to move in that direction. That's the basics of the law of inertia, right? And when I say an unbalanced force, it doesn't mean that you're like, you've got something sitting on a scale and all you need to do is tip the balance, you know, and all you need to do is make that scale not balanced anymore, and there you go, you've got an unbalanced force. It simply means that there are forces constantly acting on every object in the universe. And so the unbalanced force is just one of the forces, or maybe even two of the forces that you have constantly acting on you, changes the dynamic by being a larger proportion of the forces acting on you, and thus makes you move in a specific direction, right? So the law of inertia, any object at rest or in motion will remain at rest or in motion until acted upon by an unbalanced force. The law of equal but opposite reaction, every action has an equal but opposite reaction. And then the law of gravity is the third law, and basically that just has a formula associated with it that's got the relationship between mass and gravitational force. Even though gravity, as we understand it now, according to Sir Isaac Newton's understanding, was flawed, because he actually thought of it as a legitimate force rather than a phenomenon created by the, shall we say, like I said earlier in the theory of general relativity, warping of space-time. All right. Now, other scientific laws that we have are laws of conservation of matter and energy. Matter and energy, both, cannot be created or destroyed, merely transformed into new forms. Whether that be, you know, energy going from chemical to potential to kinetic to thermal, any of those, you know, energy will transform into different forms, but no matter what, the same amount of energy exists at any given time in the universe. Same with matter. The same amount of matter will always exist at any given time in the universe. We have been unable to, in any of our best attempts, destroy matter. The closest we've ever come to destroying matter was actually transforming matter into energy through nuclear fission. And that's a conversation for another time, but basically matter and energy also have an intensive relationship together, not just with themselves, you know, matter having the inability to be created or destroyed, and energy having the inability to be created or destroyed, but we've also discovered a link between matter and energy that is much deeper than, you know, simply energy can act on matter and matter can absorb energy and stuff like that. So, and then other scientific laws are the laws of thermodynamics, which basically the laws of thermodynamics help us to understand energy and its and how, like, the laws of thermodynamics are exactly what tell us that you cannot have a perpetual motion machine, right? Because energy is constantly being lost to its environment. No matter what matter or energy, you know, no matter what matter exists, it's constantly losing energy to its environment. There's no system that we have found that maintains energy all the time, right? The universe contains energy in all of its forms at all times, but there's no energy that stays in the same exact form all the time. It's always transforming, and but also being lost whether it be radiating out into the universe, or whether it be, you have friction, so the surface that you're rubbing together is going to slow down the movement that you're making, right? So you have, your Newtonian laws of physics, your laws of conservation of matter and energy, and your laws of thermodynamics. They're all examples of scientific laws, and they are scientific laws because scientific laws are proven to be correct almost 100% of the time. Almost every time you test it, you can use the scientific laws. You can trust that the scientific laws will give you the same result almost all the time, right? So, scientific laws are right, and this is a big word, almost 100% of the time. Almost is the big word. Because we can observe that nothing that we have no perfect theories and no perfect laws, that because they're subject to the same flaws that we have, which is that we cannot fully observe every single thing in the universe to be able to understand every single thing to the maximum extent possible. We can only guess at what we think is going on. No matter how much we think we understand about the stars, we are nowhere near able to fully understand why stars do what they do, how stars do what they do, and what makes a star work the way that it does. We have very educated guesses on that, but at the end of the day, the only star that we can directly interact with and directly test is our own sun. We can't directly test any other star. We are nowhere near being an interstellar species. We're not even capable of, having manned adventures to the other planets in our solar system. And we've barely gotten a piece of equipment out of our solar system. And it's not even out of our solar system. Okay? The Voyager 2, I think it is. Voyager 2 had just passed the Kuiper Belt. Now, we'll cover, the solar system and its general orientation and as well as layout. We'll study that in a later episode. But simply put, the Kuiper Belt is like the asteroid belt, but for comets, and it just lays just beyond the orbit of Pluto, right? And since comets are so small in relation to planet-sized objects, right, the Kuiper Belt can't be observed, but we know that objects would have to be in something like the Kuiper Belt to have their regular orbits, right? So comets that we can consistently observe, like Halley's Comet, or Halley, or however you want to say it. Halley's Comet can be observed every 73 or 74 years or something like that. Well, this Halley's Comet has to be in something like the Kuiper Belt in order for it to have such a regular orbit. And we've observed other comets that have somewhat regular orbits that would have to be in, that kind of area. So you have a bunch of comets that sit outside of our solar system in the Kuiper Belt. Simply put, there's another massive amount of comets. In theory, once again, we have not been able to directly observe this, but in theory, there's another massive amount of comets that form a gigantic sphere around the sun that we call the Oort cloud. And Voyager 2 is going to take probably decades, traveling faster than a supersonic bullet, faster than any airplane we've ever created, multiple times faster, by the way. Like, hundreds of, hundreds of times faster than anything you and I can imagine. This object is moving through space so fast that if you were to see it pass by you, you wouldn't see it pass by you. It would barely even be a blur to you because of how fast it's moving. And this object just got to pass through the Kuiper Belt after traveling for nearly 50 years, I want to say. It was released in, I want to say it was launched in the 70s, but it's been traveling for the better part of 50 years, and it just passed the Kuiper Belt. And the Oort cloud is many hundreds of thousands of, and hundreds of, well, not hundreds of thousands, hundreds of millions, if not billions of miles to travel yet. So it's not going to be out of our solar system until it gets out of the Oort cloud, and it's already not able to communicate with us anymore. So we will really have no ability to say whether or not Voyager 2 even survives the Oort cloud, because at that point in time, its nuclear reactor will have gone cold, and it will not be sending any more transmissions. If I don't believe that it's already done so. So Voyager 2 is already pretty much done giving us any information. But that's the furthest we've gotten. And it's a completely unmanned anything. There's nothing that we can do with that now. And it takes so long for the information to, reach us as well, once it gets past a certain point, that we'll be receiving updates on it. Even if it is still communicating with us, it will be receiving updates on it so far after the fact, right? That we won't be able to help it avoid anything or dodge a literal planet-sized object. So, but scientific laws are right almost 100% of the time, according to how we observe them, because we live in a tiny part of the universe. We cannot be sure of everything that we think. Astronomers, no matter how good they are at their job, only know so much. And the rest is conjecture, based on observations of objects that we can't test directly, that we can't interact with directly. So, science is always changing, but it's not necessarily going to be 100% accurate 100% of the time. And, no matter how good the scientific law you tested, no matter how accurate it is, at the end of the day, it's still a creation of humanity. So it's still as flawed as the ones that created it. Now, moving on to these types of measurements as our last part of the lesson today, you have quantitative and qualitative measurements. And this is going to be a huge thing when you're testing for your scientific method. These go very much directly involved in your testing of the scientific method, right? So a quantitative measurement is something that can be replicated because you're giving a defined amount of something. So a quantitative measurement is your milliliters, liters, centimeters, meters, heck, even gallons, and teaspoons, and tablespoons, right? These are all things that I can replicate if I write down the processes that I've gone through. These are quantities. I'm going to write that a little bit better so that you guys can, if you take a screenshot, it'll be helpful, right? So, the difference between quantitative and qualitative measurements is really, if you boil these two words down to their roots, you have a quantity versus a quality. And a quantity, like I said, centimeters, meters, milliliters, liters, cups, etc., etc. Right? And quality is good, bad, ugly, etc. Right? So a quantity is something that can be replicated and measured. A quality is a subjective measurement. So from my perspective, I think that flower on that tree smells really nice. That means nothing. I have made a statement about something, and I have launched an opinion about something, but that means nothing. I can't measure how nice that smells. I can take like a poll or something like that, and this is the only situation where qualitative measurements are better, is when you're asking public opinion on something, right? So public opinion on something, well, obviously an opinion is going to be qualitative. You can have things that are quantitative that help you with your opinion, but the opinion itself is a qualitative measurement. Your opinion of whether or not so-and-so is a good politician, or that company makes a good product, right? Your opinion of that is itself qualitative, but you can make quantitative measurements effective in your opinion. Like, I can say, if somebody asks me, how do you like your new car? I can say, well, my last car, I never had to take, I got 90,000 miles out of that thing before I ever had an engine issue. And this car, I've driven it 40,000 miles, and it's already got, I've already had to replace this, and this. Well, now I've got a quantitative thing that I can actually measure. I got 90,000 miles out of my last car before I had to get any work done. Whereas this car, I've gotten 40,000 miles, and I've had to have much more work done. So you can have quantitative things that go into your opinion, like when people talk about shrinkflation, right? Everybody's mad about inflation, and yes, it's not a great thing. But at the end of the day, what they're more mad about is going to be a phenomenon called shrinkflation, where you're paying the same amount. And this is how companies will often try to dodge raising their prices, is a process called shrinkflation, where they make the products smaller so that the price can remain the same, but the product loses weight or becomes smaller and less valuable, right? Less of a value, I should say. And like I said, now you have the quantity versus a quality, and this is really where quantitative measurement and qualitative measurement come into. So I can say, hey, I thought that book was good. That means nothing, though. Like, it means something for something that you can only measure qualitatively, like the quality of a story or something like that. But when it comes to testing something, and when it comes to measuring something, qualitative measurements mean nothing. You need to have quantitative measurements in order to be able to replicate your you need to be able to replicate the tests, and if you have qualitative measurements, you'll never be able to replicate the test without having that person there and them not have their biases. And that's the other problem with the qualitative measurements, is these are very subject to biases. Bias city, man. Qualitative measurements are bias city. Because nobody's ever going to be completely subjective with their opinion. And that's all qualitative measurements are. Qualitative measurements are opinion. Quantitative measurements are, well, actual measurements. So there you are. There's our first episode into science. If you do have any questions, please feel free to contact me on Twitter at Shinrai Sensei 15. And if you have questions about something I didn't cover today, please feel free to still ask me questions at Shinrai Sensei 15. I am working on setting up everything for the Q&A live streams and waiting to get a little bit more interaction before I decide to start the live streams. I'm also going to look at, once I do start getting some interaction and getting some momentum built up, we will be moving into hopefully being able to do like listener slash viewer live streams where maybe one or two of you guys can come on and actually ask me questions. And I think this will be more helpful with the English. We can, I can work with you guys on speaking English. Going to be doing on Rumble, I will be doing a fitness live stream 2 hours a day every single day of the week. The Q&A live stream will only be Monday to Friday as stated in the introduction video. And if you guys do want me to cover specific topics, please, once again, at Shinrai Sensei 15 at Twitter. And I look forward to hearing from you guys. Please, if you have any questions too, I will try my best to keep up with comments. Thank you guys so much for watching, and have a great rest of your day.